Hello friends, I am Nirbhay Gandhi and today we will be learning about types of binary codes. Classification of binary codes. The codes are broadly categorized into four categories: weighted codes, non-weighted codes, binary coded decimal codes, or we simply tell it as BCD, alphanumeric codes, error detecting codes, and error correcting codes. We start with weighted codes. So weighted codes, and these weighted codes are further categorized into three types: 8-4 -2 -1 coding, 2-4-2-1 coding, and third BCD or 8-4-2-1 coding. So we start with BCD coding. BCD coding. It's most commonly used for decimal digits to represent in binary form. A decimal number in BCD is same as its equivalent binary number only when the number is between 0 to 9. A BCD number greater than 10 looks different from its equivalent binary number even though both contain 0 and 1s. It is important to realize that BCD numbers are decimal numbers and not binary numbers, although they use bits in their representation. The only difference between a decimal number and a BCD number that decimal numbers are written with the symbols 0, 1, 2, 3, 4 and so on to 9. These are more user-friendly symbols, but BCD numbers use binary codes as their representation: 0000001 for 1, because these codes are more user-friendly to computers, but the decimal value is exactly the same. So here we take an example. For example, number 347. It's a decimal number. So first we are representing this number into its BCD equivalent. How we will represent this number is we will write the BCD form of each decimal digits, like BCD equivalent of 3, BCD equivalent of 4, and similarly BCD equivalent of 7. And beside it, this is written the binary form of 347, just to show that the BCD form and binary form are two different, although both contain 0 and 1. So now I have also drawn a table with with the decimal digits and its equivalent binary digits. So you can see 0, 1, 2, 3 means all decimal symbols and its equivalent binary digits. And also now further it's more easy to introduce another coding. That is 8-4 -2 -1 coding. It is more similar to BCD coding only, and just how we give weight to each digits, it's different. Okay, we will take one example, it would be more clearer. Let us take decimal digits 5. So how we represent 5 in BCD form, it's like this: 0, 1, 0, 1. But how we represent 5 in 8-4 -2 -1 is 8 -2 -1. It's 8 -3, 5. Similarly, so we will give weight to 8 -2 -1 and no weightage will be given to 4. That's why 1011. So now we start with 2421 coding. It is a bit complicated code, but no problem, we'll try to understand it. So for 2421 code, first we will write all the decimal digits, and 2421 coding, we will write its equivalent weighted form. For example, for 0, no weightage would be given to any of the bits, so obviously it will be 0000. For 1, weightage would be given only to 1, so how we will write it? 0001. But for 2, we have two possibilities. We can either write it as 0010 or we can give weightage to this 2, that is third bit, or we can either give weightage to MSB and we can write it as 1000. Now which one to consider? So we have rule for that. We will write the hexadecimal equivalent of these two possible combinations. So we know that for first combination 1000, its hexadecimal equivalent is 8, and for 0010 its hexadecimal equivalent is 2. Obviously 2 is minimum value, so we will consider the second combination and we will write it as 0010. Similarly, we will do it for 3 and 4. But after 4, the story changes. Now we will consider an imaginary line after 4, and now the numbers after 4, that is 5, 6, 7, 8. We will start pairing these number with the decimal number in its mirror position. Okay, so we will consider this imaginary line as a mirror, and in mirror position, whatever decimal numbers would be there, we'll start pairing with this number. So now, after pairing, what we will do is we will take 9's complement of that paired number and we will write it as it is. It will be our 2421 coding for that number. We will take an example. Let us take 7. 7 is paired with 2 and 2 is written as 0010. Now we will take 9's complement of this number. 2 is 0010, taking 9's complement will be 1101. So here it is 1101. Okay, so this is how we write 2421 coding, and you can check with all the numbers. Now second category is non-weighted codes, and also non-weighted codes are categorized into two: XS3 code and gray code. So XS3 code. Now XS3 code, how to represent a number in XS3 code is first decimal numbers 0, 1, 2 to 15, and binary equivalent, 4-bit binary equivalent of this number. Now it is a very easy code. The only thing we have to do is just we have to add 3 to its binary equivalent. Now for example, for 0 we will do to write its XS3 code, what we will do is 0 plus 3. 0 plus 3 gives 3, and we will write it in binary form, it's 0011. Similarly, for 2 we see 2 plus 3, it's 5, and after binary addition we get 5. That will be simple, for that will be applicable on all the binary digits till 12, because after 13, after 12, let's say 13, if we add 3 to it, the number will be above 15, and the number above 15 requires 5-bit binary representation. So we just represent these number with don't cares. Now on moving further, gray code. Now how to represent a binary code into its equivalent gray code? We have a binary number and its binary bits. These are its binary bits, B3, B2, B1 and B0. Now how to represent it into its gray code is the MSB of gray code will be same as the MSB of binary code, that is B3 would be same as G3. Now we have to find G2, G1 and G0. How to find G2 is we will perform a XOR operation between B3 and B2. That will be our G2. Again for G1 we will perform a XOR operation between B2 and B1, and similarly for G0 we will perform a XOR operation between B1 and B0. So here for reference I have also provided a XOR truth table. It will be useful in our next table where actually we are representing binary bits in its equivalent gray coded bits. So it will be more helpful in our next slide. So yeah, let's move towards our next slide. Now here we have decimal numbers 0 to 15 and its binary equivalent. So we know very pretty well that how to represent a decimal number into its binary equivalent. So now how to represent it in gray code is, first, now rule number one, the MSB of this binary equivalent would be same as the MSB of gray code. So 0 is the MSB of binary equivalent of 0, decimal number 0. So we'll be writing same as MSB of gray code. Now what for G3, G1 and G0? So for G3 we will perform XOR operation between these two, 0 and 0. 0 and 0 XOR operation is 0. So we can also refer our XOR truth table, and again XOR operation between 0 and 0 will be 0, and XOR operation between 0 and 0 will be 0. Okay, we'll see another example. It will be more clear. Now we have decimal number 9. So how to represent decimal number 9 in its equivalent gray code? Rule number 1, the MSB of this binary equivalent will be the same MSB of gray code. So 1 is the MSB of binary equivalent. We will write 1 as it is. Now we will perform XOR operation between 1 and 0. XOR operation between 1 and 0 is 1. So we'll write 1. Then again XOR operation between 0, 0. XOR operation between 0, 0 is 0. Again XOR operation between 0 and 1. XOR of 0 and 1 is 1. So 1, 1, 0, 1 is its gray code equivalent. So moving on towards alphanumeric codes. Alphanumeric codes, these represents numbers and alphabetic characters. Mostly such codes also represent other characters such as symbol and various instructions necessary for conveying information. For example, ASCII, very well known alphanumeric codes, American Standard Code for Information Exchange. Then second is EBCDIC and BU code. So we'll just have a look at ASCII code. So yeah, this is ASCII code, and we can see that the alphabets are starting with capital alphabets are starting with the decimal number 65, and also small alphabets from A are starting with the decimal number of 97. So yeah, this is ASCII code. So moving towards next coding, error codes. Now, what is error? Error is a condition when output information does not match with the input information. During transmission, digital signals suffer from noise that can introduce error in the binary bits traveling from one system to other. That means 0 may change to 1 and 1 may change to 0. To avoid these kinds of error, we use error detecting codes, which are additional data are added to a given digital message to help us detect if an error occurring during transmission of a message. A simple example of error detecting codes is parity check. To detect and correct the errors, additional bits are added to the data bits at the time of transmission. The additional data bits are called parity bits. These allow detection or correction of the errors. Now, parity checking for error detection. It is the simplest technique for detection and correcting errors. The MSB of an 8-bit word is used as the parity bit, and the remaining 7 bits are used as data or message bits. The parity of 8 bits transmitted word can be either even parity or odd parity. Now, what is even parity? Even parity means the number of ones in the given word, including the parity bits, should be even. And odd parity means the number of ones in a given word, including the parity bits, should be odd. Now, how does error detection takes place? Parity checking at the receiver can detect the presence of an error if the parity of the receiver signal is different from the expected parity. That means if it is known that the parity of the transmitted signal is always going to be even, and if the received signal has an odd parity, then the receiver can conclude that the received signal is not correct. If an error is detected, then the receiver will ignore the received byte and request for retransmission of the same byte to the transmitter. We have an example. The transmitted codes have 4 number of ones. So it is even, so 4 number of ones means even number of ones, means it is even parted code, and the received codes has odd number of ones, that is only 3. So it is odd parted code. So we can conclude that this code has been disturbed somewhere. So being a receiver, we can request the transmitter to again retransmit the same code, same byte, same signal. So that's all. Thank you so much, guys.